Hello everyone, welcome to lesson 10 of our control theory course. In this lesson, we introduce the transfer function, a powerful tool that describes the input-output behavior of a linear system in the Laplace domain. Every dynamic system maps an input signal u of t to an output signal y of t. We write this as y of t equals s of u of t, where s is the system operator. The operator captures everything the system does to the input. There are three fundamental operators. First, proportional gain, where y equals k times u. Second, the integrator, where y equals the integral of u. And third, the differentiator, where y equals the derivative of u. Every linear system can be built from these basic blocks. Now, we move from the time domain to the Laplace domain. Recall that the Laplace transform converts a time function into a function of the complex variable s. A derivative becomes multiplication by s, and an integral becomes division by s. This turns differential equations into algebraic equations. Consider a general linear time invariant ODE. The left side has output derivatives up to order n, and the right side has input derivatives up to order m. Applying the Laplace transform with zero initial conditions, every derivative of y becomes a power of s times y of s, and similarly for the input side. After Laplace transformation, we can factor out y of s on the left and u of s on the right. The ratio y of s divided by u of s gives us the transfer function g of s. It equals b of s over a of s, where b is the numerator polynomial and a is the denominator polynomial. We represent the transfer function as a block diagram. Input u of s enters a rectangular block labeled g of s, and the output y of s exits. This simple notation tells us the complete input-output relationship. The output is simply g of s times u of s. A few important properties. The order of the transfer function is n, the degree of the denominator. The relative degree is n minus m. If the relative degree is positive, the transfer function is strictly proper. If it is zero, the function is proper. Proper and strictly proper transfer functions are the most common in practice. Let us see an example. For an RC circuit with input current and output voltage, the differential equation is C times dy by dt plus 1 over R times y equals u. Applying the Laplace transform gives scy of s plus 1 over r times y of s equals u of s. Solving for the ratio, g of s equals 1 over s c plus 1 over r. This is a first-order transfer function. Now consider an RLC circuit. The differential equation is second order. C times d squared y by dt squared plus 1 over r times dy by dt plus 1 over l times y equals du by dt. The Laplace transform gives g of s equals s divided by s squared c plus s over r plus 1 over l. This is a second-order transfer function. For the DC motor we studied earlier, the system has multiple loops. Each loop has its own transfer function block. The integrator 1 over LAS represents armature inductance, gain C phi F converts current to torque, and integrator 1 over JS represents the mechanical side. By combining these blocks, we can derive the complete motor transfer function. Notice something important. We replace the integrators in the time domain block diagram with their Laplace equivalents. An integrator in time becomes 1 over s in the Laplace domain. The gain blocks remain the same and the overall structure is preserved. This gives us a clean transfer function representation. Excellent. In this lesson, we learned that the transfer function g of s captures the complete input-output behavior of a linear system. It is the ratio of output to input in the Laplace domain. We saw examples for RC, RLC, and DC motor systems. In the next lesson, we explore impulse response and convolution. See you there.